Right now, this exact second, while your eyes move across this line and these shapes turn into meaning somewhere behind your forehead, you are doing something that, if one of the greatest physicists of the last 100 years is right, no computer will ever be able to do. Not a faster computer, not a smarter one, not some future artificial intelligence 1,000 times beyond anything we have today. Not a quantum machine the size of a moon. Ever. Something about the way you just understood that sentence may be, in the strict mathematical sense, impossible to program. And I want to be careful here because that sentence sounds like the kind of thing you'd find printed on a candle in a wellness shop. Your mind is not a machine. You are more than atoms. There is something special in you no science can touch. Very soothing. Usually complete nonsense. Except this time it isn't a mystic saying it. It's Roger Penrose, the man who proved, working alongside a young Stephen Hawking, that black holes are not just the mathematical curiosity, but something the universe is actually forced to make. A knight, a Nobel laureate, one of the last living people you could reasonably call a giant of 20th century physics. And in 1989, he wrote a book that made a lot of his own colleagues wince, because at its center was that same embarrassing claim: that your mind is not a machine. But Penrose didn't argue it with poetry. He argued it with a theorem, a cold, airtight piece of mathematical logic from 1931, a proof that had already, decades earlier, quietly demolished one of the grandest dreams in the history of thought. And Penrose noticed something about that proof that almost nobody wanted to notice. He noticed that if you turn it around and point it at the human brain, it seems to say that whatever you are doing when you understand something, really understand it, is not calculation, is not computation, is not, in principle, anything a machine could ever be built to do. I have to tell you up front, this video does not end where you think it does. It starts as a story about the brain. It does not stay one. Follow Penrose's thread far enough, and it pulls you clean out of neuroscience and drops you into the single deepest unsolved problem in all of physics. The place where every equation we have breaks down, and it leaves you standing there, holding the strong suspicion that the question, what is consciousness, and the question, what is reality actually made of, might turn out to be the same question, with the same answer, living at the same address. And I should warn you about one more thing. For about 30 years, this idea was treated as one of the most ridiculed, quietly embarrassing positions a serious scientist has ever taken. Physicists had a knockout argument against it. They used it. They moved on. Which is exactly why what has happened in the last 2 or 3 years is so strange. Because the corpse started twitching. Hold on to that. We'll get there. Let me earn it first. Okay, let me back all the way up, and let me start with a thing you already believe. The safe thing. The thing that, honestly, I believed too, without ever once examining it. The brain is a computer. Obviously, right? It's the most magnificent computer in the known universe. A wet 3-pound machine with something like 86 billion neurons, each one connected to thousands of others, firing or not firing, on or off, 1 or 0. That's a switch. That's a transistor made of meat. And when you get enough switches wired together in a complicated enough pattern, you get this. You get thought. You get me talking. You get you understanding. Consciousness is just what a sufficiently complicated computer feels like from the inside. This is more or less the default worldview of our entire technological age. It's the assumption underneath every headline about whether the new AI is becoming self-aware. Different hardware, same software. Brains and machines running the same kind of process, just in different materials. And Penrose looks at that entire comfortable picture and says, no. Not just I doubt it. Not just it feels wrong. He says he can show you, with mathematics, that it cannot be the whole story. That there is a specific thing your mind does, the act of understanding, that no computer, by its very definition, is able to do. To feel the force of what he's claiming, I need to take you back to 1931 and to a shy, brilliant, deeply strange Austrian logician named Kurt Gödel. And I need to tell you what he broke. Bear with me here, because this is the load-bearing wall of the whole video. If you get this, everything after it lands. So let me build it slowly. At the start of the 20th century, the smartest mathematicians alive had a dream. A beautiful dream. The dream was that all of mathematics, every truth about numbers, every theorem that has ever been proven or ever could be captured inside one perfect system. A finite set of starting assumptions, the axioms, plus a finite set of rules for grinding out new truths from old ones. And the promise was that this machine, this system, would be complete. Every true statement about numbers could, in principle, be reached by turning the crank. And it would be consistent. It would never, ever grind out a contradiction. A perfect, closed, airtight cathedral of reason, where truth and proof were the same thing. The greatest mathematician of the age, David Hilbert, made finishing this cathedral the central mission of the field. Let me give you a way to feel what a system like that actually is, because the word system sounds abstract, and it isn't. Imagine a game. A completely mechanical game. You've got a starting position and a rule book, and the rule book is so precise, so utterly free of judgment, that you could hand it to someone who does not understand a single thing about mathematics, who doesn't even know what the symbols mean, and they could still play it perfectly. They just match patterns. If you see this arrangement of marks, you're allowed to write down that arrangement of marks. That's it. No insight required, no understanding required. That mindlessness is the whole point. That's what makes it a machine. That's what makes it, in the deepest sense, a computer program. An algorithm is exactly this: a rulebook so complete that a person who understands nothing can follow it and never go wrong. The dream was to build a rulebook like that, big enough to generate all of mathematics. Then along comes Gödel, 25 years old, and he doesn't just fail to finish the cathedral, he proves it can never be finished. By anyone. Ever. Here is what he did, and I'm going to give you the soul of it rather than the machinery, because the machinery is genuinely brutal. Gödel found a way to make mathematics talk about itself. He invented a code, a way of turning statements about numbers into numbers themselves, so that a mathematical statement could secretly be a statement about mathematical statements. And using that trick, inside any system powerful enough to do basic arithmetic, he constructed one particular sentence. And that sentence, decoded, essentially says of itself, this statement cannot be proven within this system. Now sit with that for a second, because it's a trap, and it's a perfect one. Ask yourself, is that sentence true or false? Suppose the system can prove it. Then the system has proven a statement that says it can't be proven. So the system has proven something false, which means your beautiful, consistent cathedral just contradicted itself. It's broken, worthless. So if the system is any good, if it's consistent, if it never lies, then it cannot prove that sentence. It's stuck. The sentence sits there, unreachable, forever outside the system's grasp. But now look at what that means. If the system can't prove it, then the sentence is telling the truth. It says it can't be proven, and indeed it can't. So the sentence is true. A true statement about numbers. That the system, by its own iron logic, can never reach. And this isn't a flaw in one particular rulebook that a cleverer mathematician could patch. This is Gödel's hammer blow. It works on any rulebook. Any consistent system strong enough to describe arithmetic will always contain true statements it cannot prove. Make the system bigger. Add the unprovable truth as a brand new axiom. Doesn't matter. Gödel's method just builds you a fresh, unreachable truth for the new, bigger system. The cathedral can never be finished, because the act of finishing it is impossible. Truth, it turns out, is strictly bigger than proof. Forever. That was 1931. It is, no exaggeration, one of the most important things any human being has ever discovered. It ended Hilbert's dream in a single stroke, and for 60 years it lived mostly inside mathematical logic. Admired, terrifying, a monument. And this is where Penrose does the thing that made his colleagues wince. Because here comes the move. Watch closely. Penrose says, wait. Look at what just happened in your own head. You, a human being, not a formal system, a person. You just looked at that Gödel sentence and you saw that it was true. I walked you through it a minute ago. You followed it. You understood why it has to be true, precisely because it can't be proven inside the system. But the system itself, the machine, the rule book, can never reach that conclusion. It's forbidden to. It's outside the wall for the machine. You just stepped outside the wall. So whatever you were doing when you understood that the Gödel sentence is true, that act cannot have been the machine grinding through its rule book. Because the machine provably can't get there, and you provably did. Which means, Penrose argues, human understanding is doing something that no fixed algorithm can do. Your comprehension is not the execution of a program. It reaches truths that no program following its rules could ever certify. And now, watch the dominoes, because they fall fast. If understanding is non-computable, if it genuinely can't be captured by any algorithm, and if the brain is the organ that produces understanding, then the brain must be doing something that no computer can do. Something non-computable. But here's the problem. Here's where it stops being about the brain and starts being about everything. Every physical law we currently possess, every equation in physics, from Newton to Einstein to quantum mechanics, is computable. That's what an equation is. You put in the numbers, you turn the crank, you get the answer out. A good enough computer can simulate all of it. So if the brain is doing something non-computable, then the brain is doing something that our known physics cannot describe. That's the trapdoor opening under the whole conversation. You came in to talk about neurons, and Penrose has just quietly informed you that if he's right, there is physics we do not have, hiding somewhere inside your skull. Now, I promised you honesty, and this is exactly the moment to be honest. Because if I just kept escalating and didn't stop here, I'd be selling you something. You should be resisting right now, and a lot of very serious people resisted, hard. So let me play the skeptic, out loud, as fairly as I can, because the objections are good. You might stop me and say, hang on, how do I know the system is consistent? Gödel's trick only works if the system never contradicts itself. Maybe the human mind is itself just a formal system, one that happens to be inconsistent or unsound, occasionally wrong. Human beings believe false things constantly. Maybe you didn't transcend the algorithm. Maybe you're just a sloppier algorithm that can't even tell when it's being unreliable. That's the objection the philosopher and logician crowd hit Penrose with the hardest, and it has teeth. You can't step outside a system to prove its consistency from the inside. Gödel proved that too. So maybe your sense that you saw the truth is exactly the kind of overconfidence a flawed machine would have. And there's a second objection, subtler, and in some ways, nastier. Sure, you saw the truth of that one Gödel sentence, but maybe you're just a bigger machine, a different, more elaborate rulebook that happens to include a rule for handling Gödel sentences. And then there'd be a new Gödel sentence for you, the bigger machine, that you couldn't see through. And you'd never even notice because it's your blind spot by construction. The machine can't see its own blind spot. Maybe you can't see yours. Maybe you just haven't met your Gödel sentence yet. I find these objections genuinely strong. I want to be clear about that. The consensus among logicians and philosophers of mind is that the Gödel argument as a strict proof does not work. That Penrose is smuggling in an assumption, namely that we can somehow know our own reasoning is sound and consistent. And that assumption is the very thing in question. Douglas Hofstadter, who wrote the sprawling, beautiful, Pulitzer-winning book Gödel, Escher, Bach, which is the reason a lot of people, me included, first fell in love with this whole area. Hofstadter thinks Penrose is flatly wrong here. He thinks self-reference and strange loops in an ordinary computational system are enough to give you a mind. No exotic physics required. Two brilliant people, looking at the same theorem, walking in opposite directions. So I'm not going to tell you Penrose won the argument. He didn't. Most experts think he lost it. What I'm going to tell you is something more interesting than winning. I'm going to tell you what he did next, because a normal scientist, faced with that wall of expert disagreement, backs off, hedges, says, well, it's suggestive. Penrose did the opposite. He took his own conclusion completely seriously and asked the insane follow-up question. He asked, okay, if the brain really is doing something no known physics can compute, then where, physically, is the non-computable stuff coming from? Where in the universe is there a crack big enough for it to hide in? And his answer to that is where this stops being a philosophy seminar and becomes one of the strangest ideas in modern science. Because there is a crack. There's one place in all of physics where our equations genuinely, admittedly, break down. Where the smartest people alive will tell you, if they're honest, that they do not know what is happening. And it is not some obscure corner. It is sitting right at the heart of our most successful theory ever built. It's the measurement problem in quantum mechanics. Let me set this up because you need to feel the weirdness for the payoff to hit. In the quantum world, before you look at it, a particle does not have a definite location. This is not a poetic way of saying we don't know where it is. It genuinely does not have one. It exists in what's called a superposition, a real physical smear of every possibility at once, here and there and everywhere, all overlapping, all real, described by a mathematical object called the wave function that evolves smoothly and, crucially, computably following an equation we understand perfectly. An electron can be, in a completely literal sense, in two places at the same time. This isn't speculation. We build technology on it. But then you measure it. You look. And in that instant, the smear vanishes and the particle is just here. One place, definite, real. The way everything looks in ordinary life. And here is the scandal at the center of physics. The thing that should be a much bigger deal in the public mind than it is. Nobody knows what that transition is. Nobody knows why, or how, or when the shimmering maybe becomes a solid is. The smooth, computable equation describes the smear beautifully. It says absolutely nothing about the moment the smear collapses into one answer. That collapse, the most common event in the universe, happening trillions of times a second, everywhere reality touches itself, is not in the equations. It's bolted on by hand. Physicists have argued about it for 100 years, and there is no agreement. It's the open wound of the whole subject. And Penrose looks at that open wound, that one admitted gap where our computable physics runs out, and he says, there. That's where it lives. That's my crack. Whatever makes the wave function collapse, whatever turns maybe into is, that process is not described by any equation we have. And Penrose makes a specific, bold bet about it. He bets that the collapse is a real, objective, physical event. Not something a conscious observer causes by looking, which is one popular interpretation, but something the universe does on its own, triggered by gravity. His idea, roughly, is this. A quantum superposition is, in effect, a tiny region of spacetime being asked to curve two different ways at once. Because mass curves spacetime, and a particle in two places means its gravity is pulling two ways at once. And spacetime, Penrose argues, can only tolerate that split for so long before it becomes unstable and has to snap into one option or the other. The bigger the mass involved, the faster the snap. And, this is the whole ballgame, he conjectures that the specific way it snaps, which possibility it lands on, is governed by the missing theory of quantum gravity. The theory we don't have. The theory that, he suspects, will turn out to contain non-computable elements. Something no algorithm can predict because it isn't running an algorithm. Do you see what he's done? He has taken the non-computable something he thinks he found in human understanding, and he has found it a home in the deepest unsolved problem in physics. He's welded the mind to the measurement problem, the place where you understand meaning and the place where the universe decides what's real. Same missing physics, same crack. And I remember when I first followed this chain all the way through, I had to put the book down and just walk around my apartment for a while. Because whether or not it's true, and hang on, we're getting to whether it's true, it is one of the most audacious single ideas I have ever encountered. It says, the reason you are not a computer, and the reason a quantum particle becomes real when it's measured, are the same reason. That is either profoundly wrong or one of the great insights of the century, and there is not a lot of room in between. But Penrose had a problem, a physicist problem. It's a gorgeous idea, but the brain is warm and wet and enormous compared to a single electron. Quantum effects, superpositions, that delicate, smeared-out coherence are famously fragile. Bump them with a little heat, a little noise, a stray molecule, and they collapse instantly. That's why building a quantum computer requires cooling it to near absolute zero and shielding it from basically everything. So, how on earth could your hot, sloshing, chemical brain be maintaining and orchestrating delicate quantum states long enough to do anything with them? Penrose, being an honest man, admitted he had no idea. He had a where in physics, the collapse. He had no where in biology. No mechanism, no structure. And a theory of consciousness with no biological home is just a very sophisticated wish. And then he got a letter. Or rather, an anesthesiologist came to find him. And this is where the story picks up a second main character, and honestly, a better one for storytelling, because he's obsessed. His name is Stuart Hameroff, and Hameroff had spent his entire career put to sleep in the most literal way possible. He's an anesthesiologist, the person who, before surgery, gives you the drug that switches your consciousness off. And that job had left him haunted by a question most of us never think to ask, even though it is staring at every one of us every time we've ever been put under. When the anesthetic hits and you go from a person, an inner world, someone who is there, to nothing, to no one, to a gap you don't even experience as a gap. What, precisely, turned off? What is the switch? Where is it? What does the drug actually touch? Because think about it. Anesthesia is arguably the most precise tool we have for interrogating consciousness. It doesn't kill you. It doesn't stop your heart or your breathing or most of your brain's electrical chatter. It reaches in and, with eerie specificity, deletes the one thing, the awareness, the you, and leaves the machinery running. If you want to find where consciousness lives, follow the drug. Find what it grabs. And Hameroff had an idea about what it grabs. And it was not neurons, exactly. It was something inside them. Something smaller. And this is the word I told you to hold on to. The one that's going to run through the entire rest of this story. Microtubules. Let me tell you what those are, because when I learned this, I felt slightly cheated that no one had told me earlier. You probably picture a neuron as a simple blob with wires coming off it. But inside every one of your cells, inside every neuron in your head, there's a skeleton. An internal scaffolding that gives the cell its shape and acts as its transport network and its structural frame. And that scaffolding is built out of microtubules, tiny hollow tubes, exquisitely regular, made of protein units called tubulin, stacked in a precise crystalline lattice, like a rolled-up honeycomb. They are staggeringly small, around 25 nanometers across, so small that thousands would fit across the width of a single human hair. And there are, in your brain, something on the order of 100 trillion of them. A vast, hidden, crystalline architecture. One layer of reality down from the neurons everyone talks about. And Hameroff, staring at these things for years, had become convinced they weren't just girders. He thought their regularity, their crystalline order, made them look less like scaffolding and more like hardware. Like they could hold and process information at a scale far finer than the clumsy on-off firing of the whole neuron. And when he encountered Penrose's work, a Nobel-caliber physicist desperately needing a biological structure that could shelter delicate quantum states, orchestrate them, and do it inside the brain, Hameroff essentially walked up and told him he thought he knew exactly where it was happening. Not in the neurons, in the tubes inside the neurons. And out of that collaboration came the theory with the beautiful, faintly ridiculous name, Orchestrated Objective Reduction. Orch OR, objective reduction, is Penrose's gravity-driven collapse, the universe snapping the smear into one reality. Orchestrated is Hameroff's contribution, the idea that biology, the microtubules, tune and shelter and conduct these quantum states, orchestrate them, so that the collapse isn't random noise, but something structured, something meaningful. And here is their actual, specific, put-it-on-the-record claim. And I want you to really hear it, because it is genuinely one of the most extraordinary sentences in the whole history of the science of the mind. They propose that a moment of conscious experience, a single flicker of you being here, aware, literally is one of these gravitationally driven quantum collapses, occurring in the microtubules inside your neurons. And they put a number on it. Roughly 40 times a second. 40. That's the rhythm. It lines up with a well-known brainwave frequency, the gamma rhythm, around 40 cycles a second, that neuroscientists have long associated with conscious awareness and with binding your experience into a single, unified scene. 40 times every second, on this theory, the universe reaches into the tubes in your head and decides what's real. And each one of those decisions is a single frame of your consciousness. Your entire inner life, the whole seamless movie of your existence, would be a flipbook. 40 frames a second of the cosmos choosing. And you, the watcher, would be the choosing. When I first heard that, my honest reaction was, this is insane. Not insane like wrong, insane like, is this person a genius, or have they lost the plot entirely, and how would I even tell the difference? It has the exact texture of both, and I felt genuinely uneasy, because the whole thing was so seductive, so beautiful, that I could feel myself wanting it to be true. And wanting something to be true is the single most dangerous state a curious person can be in. That's when you get fooled. And the physics community felt that danger too, and they came for it. And for a while, it looked like they'd won cleanly. In the year 2000, a superb physicist named Max Tegmark, sharp, rigorous, no crank, sat down and did the thing that seductive theories most fear. He did the arithmetic. He took Orch OR's own claims and asked the brutal quantitative question. Given how warm the brain is, given how noisy and wet and crowded it is with jostling molecules, how long could one of these delicate quantum superpositions in a microtubule actually survive before the environment smashed it? Before it decohered? Before the quantum smear got scrambled back into ordinary classical mush? And his answer was devastating. He calculated a survival time of around 10 to the minus 13 seconds. Let me put that number where you can feel it, because a bare exponent means nothing to the body. 10 to the minus 13 seconds is a tenth of a trillionth of a second. And remember, consciousness on this theory needs the quantum state to last long enough to matter on the time scale of thought. Something in the neighborhood of a 10,000th of a second, maybe longer. Tegmark's number was shorter than the timescale Orch OR needs by a factor of roughly 10 billion. Not close, not off by a bit, off by a chasm. The quantum state would be dead, thoroughly, hopelessly, classically dead, billions of times over before it could do a single thing for your mind. And that was, functionally, the end of it, for a generation. The physics community exhaled. It was too warm. Case closed.
The brain was too hot for quantum magic, full stop, and anyone who kept insisting otherwise was, in the polite word, misguided, and in the impolite word that got used at conferences, a crank. Penrose was a genius who'd wandered out of his lane and gotten lost. Hameroff was the anesthesiologist with the fever dream. For years, if you brought up Orch OR among neuroscientists, the reaction was a particular kind of eye roll, the one reserved for ideas that are beautiful and dead. And I'll be honest with you, when I first read this far, I was relieved. There's a part of me that's suspicious of ideas that are too gorgeous, that flatter us too much, that whisper, "You are special. You are not a machine. You are woven into the fabric of the cosmos." Tegmark's number felt like the adult in the room. The universe doesn't owe us mystery. Sometimes the wet machine is just a wet machine. I closed that chapter feeling like the grown-ups had spoken.
And if ideas like this are the kind of thing that keeps you up at night, the moment where the tidy answer starts to wobble, where the case that looked closed turns out to have a loose thread, then sticking around here is probably a good move, because this is exactly where the story stops behaving. This channel exists because enough people would rather sit with a genuinely open question than be handed a comfortable false ending. And if that's you, come with me, because we are about to walk straight into the loose thread. Because here's the thing about that comfortable ending. It rested on a single assumption, one that everybody in the year 2000 took as obviously, unquestionably true. The assumption was this: quantum effects cannot survive in a warm, wet, biological environment. They're too delicate. Life is too messy. Period. And over the following 2 decades, that assumption quietly fell apart.
A whole new field grew up, and it has an almost self-contradictory name: quantum biology. And it studies living systems that appear to be exploiting quantum effects, the exact fragile, warm-hating effects that were supposed to be impossible outside a supercooled lab, and doing it inside warm, wet, living tissue, at body temperature, casually, as a matter of everyday survival. The cleanest, most robust example, and it kills me a little that this isn't common knowledge because it's astonishing, is bird navigation. When a robin flies thousands of miles and finds its way, the leading and increasingly well-supported explanation is that it is, in a real sense, seeing the Earth's magnetic field. And the mechanism, as far as we can tell, is quantum. Light hits a protein in the bird's eye called cryptochrome and knocks it into a state involving a pair of electrons whose quantum spins are entangled. That delicate, spooky, supposedly fragile linkage that Einstein famously hated. And the Earth's faint magnetic field nudges that entangled pair, and the bird reads the result. A living creature, warm-blooded, running a room temperature quantum sensor in its own eyeball, and using it to cross a continent. That is not a theory anymore. That is, in its essentials, happening inside a bird, right now, somewhere over your head. And once that door was open, people found more. The evidence is real, and it is also genuinely debated. I want to keep being straight with you, because in quantum biology, the hype has sometimes run ahead of the data. And some early bold claims about, say, quantum coherence in photosynthesis have been walked back and argued over hard. So this isn't a clean sweep. But the core discovery stands, and it is enough to matter. The flat, confident assumption that biology is simply too warm for any quantum effect to survive and do useful work. the exact assumption that Tegmark's knockout blow was built on turned out to be false. Nature had found ways. Structure, it turns out, can protect coherence. The right architecture can shelter a quantum state from the noise that should destroy it. And the moment that becomes clear, a very uncomfortable question raises its hand at the back of the room. If birds can do it in an eye, then the confident, case-closed dismissal of Orch OR was resting on a premise that we now know is not universally true. The corpse, the theory everyone had buried, the corpse just twitched. And then people went and actually looked, in the lab at the microtubules themselves. And this is the run of results from the last few years that made me sit up and reopen this entire question. And it's why I'm making this video now instead of 5 years ago. Because these are not thought experiments. These are measurements. First, a team studying the tubulin proteins that make up microtubules found something called superradiance. Microtubules are packed with a particular amino acid, tryptophan, and tryptophan absorbs and emits ultraviolet light. What the researchers found, and this was published in a serious chemistry journal in 2024, is that when you arrange enormous networks of these tryptophan molecules in the precise, ordered, crystalline geometry that a microtubule actually has, they stop behaving like a crowd of independent little lights. They start behaving collectively, coherently, quantum mechanically as one. Superradiance is a genuinely quantum effect, where many emitters lock together and light up faster and brighter than they possibly could on their own. And they were finding evidence of it in microtubule-like structures at room temperature, in the warm, exactly where it wasn't supposed to be able to happen. Second, another group, and this one has a detail I love, studied how energy migrates along a microtubule. They shone light on them and watched excitations travel, and they found the energy propagating farther and lasting longer than any boring classical billiard ball picture could explain. A quantum signature at ambient temperature. And here's the detail. One of the co-authors on that 2023 paper, sitting there in the author list alongside the experimentalists, is Roger Penrose himself. The theorist, decades on, watching his once ridiculed conjecture get poked at in a real laboratory. But the part that stopped me cold was what happened when they added anesthetic. When they introduced the drugs that switch consciousness off, isoflurane, etomidate, the quantum effect got damped, suppressed. The anesthetic reached into the microtubule and quieted the very quantum behavior the theory said was the seat of awareness. The drug on the surgical tray, touching the thing Penrose and Hameroff had named 30 years before anyone could measure it. And then, third, the one that genuinely gave me a chill. The one I keep coming back to. 2024, a lab at Wellesley College. The researchers reasoned like this. If consciousness really does depend on quantum activity inside microtubules, and if anesthetics work by disrupting that activity in the microtubules, then here's a prediction you can actually test. If you first give an animal a drug that stabilizes its microtubules, that makes them tougher, more rigid, harder to disrupt, then it should be harder to knock that animal out. The anesthetic should have to work harder, take longer to switch consciousness off, because you've reinforced the very structure it needs to disrupt. So they took rats. They gave some of them a microtubule stabilizing compound called epothelone B. And then they anesthetized them and simply measured how long it took each rat to go under, to lose the reflex that keeps it upright. And the rats with the stabilized microtubules took significantly longer to lose consciousness. Statistically significant. A real, measurable effect. In the exact direction the theory predicted. Reinforce the tubes and consciousness becomes harder to switch off. Now, I have to keep my promise about honesty, so let me be extremely clear about what this does and does not mean, because it would be so easy to oversell this, and I refuse to. This is one study in rats with a modest sample. It is not proof of Orch OR. There are other, more ordinary explanations for why stabilizing microtubules might slow anesthesia. Microtubules do plenty of unmysterious jobs in a cell, and you could tell a completely classical story about it. The researchers know this. Nobody serious is claiming the case is now closed in the other direction. Penrose could still be wrong. Most physicists still think he probably is. I want you to hold that firmly. But sit with the shape of what just happened. For 30 years, one theory of consciousness was treated as the embarrassing crank in the corner. And that crank theory made specific, risky, falsifiable predictions. Quantum effects in microtubules at body temperature, disruption of those effects by anesthetics, and now this, that stabilizing the tubes would resist anesthesia. And when the experiments finally got done, in the last 3 years, those predictions kept landing. Of all the theories of consciousness that got tested in a major research program on exactly this question, the microtubule quantum theory was the one that produced confirming evidence. The crackpot idea is currently the one making correct predictions, and the respectable ideas mostly aren't making testable predictions at all. That is not nothing. That is, at minimum, the strangest turn this story could have taken. And here, right here, is where I have to tell you that we have not, this whole time, actually been talking about the brain. Not really. Because step back and look at what this argument is, structurally, from a great height. We started with a question that sounds like neuroscience. How does the brain make the mind? And Penrose's answer doesn't resolve it, it dissolves it, and hands you a completely different question in its place. Because if he's right, the mind isn't a special trick the brain plays. The mind is what it feels like to be on the inside of the universe's most basic act. The act of turning maybe into is. The measurement, the collapse, the moment reality chooses. Consciousness, on this view, is not a product of the brain the way bile is a product of the liver. Consciousness is a clue. It's evidence. It's the one place where we get to experience, from the inside, the thing that physics cannot yet describe from the outside. The mechanism by which quantum possibility becomes classical fact. You came here to learn how a lump of tissue produces a person. And what Penrose is actually offering you is a suspect for the deepest unsolved problem in physics. And the suspect is you. The measurement problem and the mystery of consciousness, the question of what makes the wave function collapse, and the question of what makes you aware, are, on his account, the same question. Not similar, the same. You have been carrying in your own skull 40 times a second, a live demonstration of the thing a century of physicists have been unable to explain. That's the turn. This was never a video about the brain. It's a video about what reality is made of, and it snuck consciousness in through the side door as a witness. And I want to flag one more bridge before we close, because it's the one that makes this land in the present tense, at your dinner table, in the year you're actually living in. Right now, everyone, you, me, every newspaper, every anxious late-night conversation, is asking the same question about artificial intelligence. Is it awake? Is there something it's like to be the machine?
Is the thing on the other side of the chat window conscious, or just pretending well enough to fool us? And notice what Penrose's argument, if it holds, actually says about that. Strip it down, and his whole case is, at its heart, a claim that no algorithm, no program, no matter how vast, no matter how clever, no matter how convincingly it talks, can be conscious the way you are. Because consciousness, for Penrose, is precisely the non-computable thing. It's the thing that lives in the gap where computation runs out. Which means that these systems, which are, whatever else they are, unambiguously algorithms, computations running on ordinary, fully computable physics, would be, by this argument, provably not conscious. Not yet conscious. Not conscious but we can't tell. Provably not, as a matter of mathematical principle, forever, no matter how large they grow.
The thing that most distinguishes you from the most advanced AI on Earth might not be your memories, or your feelings, or your soul in any soft sense. It might be a theorem, a cold piece of logic from 1931. The reason you are unlike the machine could be Gödel. Whether that's true, I don't know. I really don't. I've spent this whole video trying to hold two things at once. How staggeringly beautiful this idea is, and how genuinely, seriously, it might be wrong. And I'm not going to collapse that for you at the end into a tidy verdict, because the honest state of this question is that it's open, and pretending otherwise would be a betrayal of the one thing I actually care about, which is getting it right. So let me just leave you where the science actually leaves us. Suspended. In the superposition, if you like. Here's what's strange to sit with, and I mean actually sit with it, tonight, when the lights are off. If Penrose is wrong, and he may well be, the smart money still says he is, then you are a machine. An astonishing one. A machine so complex it can fall in love and prove theorems and be afraid of dying. But a machine running on ordinary computable physics. Which means that everything you will ever think or understand or feel was in principle always calculable. Always, in some sense, inevitable. A process that could, in theory, be run on other hardware, and would be just as much you. There's a strange cold comfort in that, and a strange horror, too. But if he's right, if that thread from Gödel really does run all the way down into the microtubules and out the other side into the missing physics of quantum gravity, then something else is true. Then every conscious moment you have ever had, every single frame of your entire life, was a tiny event in which the universe reached past the edge of its own known laws. A place where, for one instant, 40 times a second, reality had to choose, and the choosing was you. Not a metaphor, a physical event. The deepest law in the cosmos, the one we don't have yet, being written and rewritten in the warm dark inside your head, continuously, for as long as you've been alive. So do this, right now, before you go. Look at your hand. Actually look at it. Turn it over. Watch it move. Somewhere in there, in the crystalline scaffolding inside those cells, if Penrose is right, 40 times every second, the universe is doing the one thing it does that we cannot explain, cannot compute, cannot capture in any equation we possess. The deepest unsolved problem in all of physics is not out at the edge of some distant galaxy or down at the bottom of a black hole.
It's here. It's the most familiar thing in your entire existence. You have never once been able to feel it happen. And you have never, for a single waking moment of your life, been without it.